files that you might want to put in your search path. I made this little chart that shows several of them. So there's media assets, movies, sound files, image files, MIDI sequences are another kind of thing you might put in your search path. And again, some objects like playlist tilde can record the absolute path to a file. So you could get away with not putting it in your search path, but then if you move the file, as we just saw, you might be in trouble. Max has a thing called snapshots, not to be confused with the snapshot tilde object that we were just talking about a little while ago for pulling a single floating point value out of a signal, but snapshots meaning saving the state of your patch. We'll talk about that pretty soon. The main thing that I have in my search path are abstractions, which we're going to talk about right in the next lesson. You can also have external objects. These have the extension .mxo on Macintosh or .mxe on Windows, and these are third-party extensions to Max written in C and compiled for your platform that provide additional functionality. Also some things that you could put in your search path or instead embed them. We've been using subpatchers so far, so that's like an abstraction that is inside your patch. You'll understand a lot more in a few moments in the next lesson. Also, you can save collection files as text files on disk, and also dict files you can save as .json or .yaml. Also, there is a feature of Max called packages. Packages are a pretty nice way of collecting together lots of things that you might want to use in Max. So here I'll go to the package manager. And it's loading. It's going to the internet. It is going to the Cycling 74 online library. And we see here's a featured package. And here's a whole bunch of packages. I guess there are now 2 pages worth of packages in this Max online library. And I'm going to pick this one, CinMat Externals. And it's a collection of Max tools created by researchers at CinMat in Berkeley, California, including myself. It has a bunch of externals, most of which I wrote, actually. It has a help patch for each of these externals. So we're just looking at the browser here. But I can say install. And in the old days, you had to download, you had to go to the internet and download these things. You had to manually put them in your search path in a certain place. And you had to be careful to keep the help patches next to the externals and the documentation and the license for it. And maybe it came with source code. And it was just kind of an error-prone process that you had to manage manually. But now it's just that one click of install. I now have it in my patch. So I can say show in file browser. And this is a thing that's built into Max. And now it's showing me all of these objects that are in it, including we used this one Resonator tilde a little while ago, which in this package, it is compiled for either Windows or Macintosh. And it's showing me the path. It's showing me that it put it inside my documents folder, in the Max 7 subfolder, inside the packages subfolder. And now that folder has a subfolder called CinMat Externals that has a bunch of stuff inside it. So let's take a look at my documents folder, Max 7. Packages, and now look, I have one package here in my folder, and it's all these files. So package is a very nice, all-in-one, convenient way of getting a package, a collection of things that were made by a third party. And now they're in the search path. So now I can go into Max and I can use the I already put resonators in my search path manually, but let's use another one of these like Well, how about OSC route? Maybe that's the best Max external ever. OSC route. So there we go. It's a real thing. I can click on the help patch. There it is. So this third-party external that comes from CinMat, whose logo looks like this, is now in my Max search path, and it's all in one convenient thing. If CinMat were to update this and release a new version, then I could just update the entire package, and it would happen in a clean way. I wouldn't have to remember where I put everything and go find everything that I previously downloaded and overwrite with a new version. Packages are very convenient, very nice. So what exactly is in a package? There's some nice documentation on this. So if you search the documentation for packages, documentation working with packages, and there's 2 guides inside about packages, which basically says a package is just a folder that has a bunch of specifically named subfolders that have certain stuff inside them. So if you have examples in your package, then you have to put in a folder named examples. If you have externals, you have to put in a folder named externals. So it's just a very logical naming convention. And you can see that this package that I got from CinMat doesn't have all of these things. It only has a subset of them, and that's fine. But whichever of these things exist in the package, you need to go in those particular folders, and then you can use the package manager like I just showed. You just click on it to install. It couldn't be much easier. And you can also remove a package. There's you can disable it. You can like put a pause on it and say, what would life be like without the CinMat externals? Let's try it. And then if you decide you'd be wrong, that you actually liked it better not having that, you could just delete that whole package and the whole thing would be gone cleanly all in one. So packages, very nice feature of Max. To review, Max can read and write all kinds of files, and we'll show soon some specific mechanisms for doing that with specific kinds of files. But any file that you want Max to be able to find has to be in the search path. You set the search path by going to the preferences and saying file preferences under the options menu. You add folders to that, and those folders anything you put in those folders, Max will be able to find. And the easiest way to do it is to use packages. If the stuff that you need is already in a package, then you can just install the package and not have to worry about any of the other details. So I've mentioned several kinds of files that you might want to put in your Max path, and you've seen a lot of examples of Max objects that can read files of those types, and there are also a lot of Max objects that can write files of those types. So I made this handy chart showing how to read and how to write several different kinds of files that are typically used with Max. So sound files. We saw that there's an object called buffer tilde that can read in a sound file and store it in memory in a way that's accessible to other MSP objects that can play back that audio in various ways. There's also an object called polybuffer tilde that can read in an entire directory full of sound files, and it'll make you one buffer for each sound file, and you can access them in various ways. That's very nice. With the buffer tilde object, you can either type in an argument. You can say buffer tilde foo my file name.wave, or you can just create the buffer tilde object and give it a name, and then later send it the message read with an argument of the file name that you want to read. And of course, you'll look through your search path and try to find that file, and if so, load it, otherwise fail. You can also write data into a buffer tilde. We've seen a couple objects like poke tilde and recorded tilde that can copy signals into buffers in Max, and if you want to save those signals in a sound file, you can send the write message into the buffer tilde object, and it'll save it. And there's also like a write AIFF and a write wave, so you can tell it what type of sound file to write by choosing the correct message. Okay, that's sound. Files. For image files, we saw jit.playlist. That is not it's not as programmable. So the object jit.movie, you can send it the message read, and it will read a movie. It can be either a still image or an actual movie clip that has a time axis. Either way, you use the jit.movie object to read it. To write a still image, if you have programmed some gorgeous thing into a jit matrix, you can send the message export image to the jit.matrix object, and it will write an image file containing whatever pixels are in that jitter matrix. If you want to record a movie output, then you use an object called jit.record that will take each subsequent frame of the movie and write it out into a movie file. We talked about dictionaries as a way of storing data, and you can either give an argument when you create the dict object, or you can send it the message import, and it will, in either case, it'll look for a file that contains the contents of that dictionary, and those files are either in JSON or YAML format. You get to decide which one you want, and it can read either one. And you can also write them. So if your program saves data into a dictionary, you can send either the message export or the message write into that dict object, and it will save it into a file. There's also the collection object call, and again, you can have either an argument that you type in to the call object, or you can send it the message read. You can also send it the message read again. So if you have been working on data in a collection in some external text editor, and you save it, and you want your max hatch to reread the collection, the data from that text file, you can send the message read again, and it will reread its current file. Also, you can send call the message write, which will write its current data into a new file, or write again. So it's kind of like save as versus save write. Will get it to, if you send it write, it wants to know the name of the file you're writing to. If you say write again, then it just it overwrites whatever file it previously read from or is reading to. You can read and write MIDI files, MIDI sequences, using either the SEQ, short for sequencer, the seek object, or the detonate object. Those are two objects that can read, play back, record, and write out to file MIDI files. So you can use Max as a MIDI recorder, or to play back MIDI sequences, or whatever you want. There's an object called patcher attributes that is sort of like the preset object. It's a way of saving the state of various objects in your patch, and you can also use it with snapshots, which is a way of saving the state of VST plugins and other such things. And there's an object called patter storage that can read and write all this data to files. And then finally, for Max patches themselves, obviously if you just type in the name of an abstraction in an object box, then you are reading in a copy of that abstraction from disk, and that is the typical way of using abstractions. I do that all the time, but you can also do it under programmatic control. So there's an object called p control that you can send it a message, and it will read an abstraction off of your search path and open that as just another patcher window that's open in Max. So you can get into a lot of trouble very quickly by writing a program that opens patchers, and you can very quickly completely fill your screen with windows by reading them off of the disk. And an even crazier thing you can do, there's an object called this patcher that you can actually use to script Max. We'll talk about that in detail how to do that in a later session. But you can send it a message that says make there be a certain object at a certain part of the screen, and you can send another message that says connect this outlet of this object to this inlet of this other object, and you can write a Max program that writes a Max program, and then you can send the write message to the this patcher object, and it will save that program that you created into a file. So that's my little table of various objects that let you read and write various types of files from Max. of this next lesson is the most important aspect of Max for my own personal style of use, namely abstractions. Already I like the name because as a computer scientist I already see life in terms of searching for, using, and refining abstractions that let me solve problems on my own terms. Many of us believe that good software, not to mention good networking protocols, derive their value largely from the abstractions that they provide. So what I mean by abstraction, here's the Wikipedia article on abstraction in software engineering, and they define it as a technique for managing complexity of computer systems. I like this little quote by John Guttag. The essence of abstractions is preserving information that's relevant in a given context and forgetting information that is irrelevant in that context. So I'll let you look at this in general to see what abstraction means to computer scientists all in all. But in Max, what I mean by an abstraction, what people call an abstraction in Max, is a patch written in Max that's meant for use inside other Max patches. In other words, it's how you write your own objects in Max. You save them in a .max path file inside your search path, just like we've been doing with all of our Max patches so far. And then when you type that name into an object box, it puts your abstraction inside that box so the rest of your program can use it. You can do this many times to create what an object-oriented programmer would call multiple instances of an abstraction. Abstractions are almost identical to subpatches, except for the huge difference that they live in separate files. That means you can edit an abstraction, for example, to fix a bug or add a feature, and then all your other patches that refer to that abstraction will suddenly start using a new version. So I'm going to start with a very simple example that just demonstrates the mechanics of the abstraction mechanism, and then we'll use it to do something much more fun and interesting in a moment. So here we are in Max. We're just going to add some numbers together. So we're going to have something that can add 10 to a number using good old plus. And what do you know? When you put in a number, 10 more than that comes out. Okay, so we're going to pretend that that's something interesting that we care about. And first thing I'm going to do is I'm going to encapsulate it. So now I have a patcher that can add 10 to numbers. And now I'm going to go into that patcher. And notice it's got an inlet and an outlet and a plus 10, which is exactly what I want. So I'm going to say save as. And I'm going to put this in my documents folder. I made a subfolder earlier called max path. It's already in my search path. And I'm going to call it plusser because it pluses. It adds 10 to something. So far, not exciting. And I actually don't even need this patch anymore because all I really wanted was the plusser part. So I'm going to not save. I'm going to make a new patch. And so here's the first thing. Now I can type plusser. And in fact, I didn't have to type all of plusser because there's a patch, P for patch, in my search path named plusser. Then it is letting me type plusser. And when I hit return, it's just like the patch that I had before. It has an inlet and an outlet. And what do you know, if I put an integer into the input, then 10 more than that comes out the output. So that's the first thing with abstractions. You save them on disk, you put them in your search path, and then you can find them in your program. And then when I was talking about multiple instances, I can duplicate all this. If you select multiple things and option click and drag, it copies all that. So now I've got 3 plussers. I can add 10 to 3 different numbers simultaneously. I could even we can go really fancy. We can compose 2 plussers side by side. So we can put 2 of them together and use that to add 20 to something. Okay, so I only made this thing once, but now I'm using it 4 times. Here's, I think, perhaps the most interesting, powerful, perhaps dangerous part of abstractions. This object is locked. And when I unlock it, I can edit it, and I can change it to add not 10, but 100. Now, when I save this, take a look over here. They're all going to sort of flash a little bit. No, they didn't. But now I just changed the definition of plusser. Plusser now adds 100 rather than 10 to something. So now all of these objects are now adding 100, except 2 of them together now add 200. So that in itself is the big idea of abstractions. You save them in a file, you refer to them from other patches, and if you change the abstraction on disk, then the patches that are referring to them change. So if these were subpatchers using P, and I copied them, in fact, let me show you that. Let's do our same thing again. We'll put an int around it. We'll make it plus 10. We'll encapsulate it. We'll have a thing that adds 10. I'll call it add 10. We can make another copy of it. And now these are totally independent copies. So this add 10 and this add 10, they're currently the same as each other. But if I change this to be 11, then now we're adding 11 to these numbers, but this is the same. I haven't changed anything. It's not referring to this in any way. It just started as a copy of it, and now it's not a copy of it anymore. Now they're different. And if I had made a whole bunch of these, and I wanted to make them all add 100 instead of all add 10, then I have to go into each one and change all these numbers to 100. Of course, I don't really want to do any of this stuff. I'm just explaining all this for the point of showing you how this mechanism works. But subpatchers are just independent. They're separate copies of each other. If you make a copy of a patcher, you just have another copy of it, and you can change it however you want, and it doesn't affect the original. Whereas with abstractions, there's only one master copy on the disk somewhere, and if you change it, it changes all of them. That's the big idea. One other thing I got to show part of the mechanics. If you double-click on a plusser object somewhere, it brings it up in this window so that you can see it. And now down here where the lock should be, there's this little pencil that says modify read only. So this is this one plusser object that I happen to click on over here, and here's this other plusser that I happen to click on. And if there's something inside it that displays something visually, you can see that they're different from each other. But if I wanted to edit it from there, having double-clicked on it and brought it up in this read-only fashion, and you notice by the way also there's this square bracket around the name of it showing you that it's an abstraction. If I click on modify read-only, now I'm editing the original version of plusser on disk somewhere. So if I make this be 1000 and save it, then boom, it's now 4:41 p.m. And plusser's date modify just changed, and all these objects are now going to add 1000 to their input. So that's the basic mechanism of abstractions. Again, you save them in a separate patch that is in your search path, you refer to them by name from other patches, and there's only one copy. It's pointing symbolically to the one master copy of that abstraction, and if you change the abstraction, then anything that uses the abstraction inherits the new behavior. So let's use abstractions to make something a little bit more sophisticated. Specifically, I'm going to make an audiovisual sine wave synthesizer. I want to start with the basic idea of a sine wave that we hear at a certain frequency, and we also are going to be able to see in our video output as a little squiggle. Sine waves has this very characteristic sound and look, so we're going to make something that can synthesize them graphically as well as sonically. And I like this idea because I can already imagine all kinds of variants that I'm going to want to try, and having them in abstractions is going to make that possible. But before we have an abstraction for it, we're going to try to figure out what we're doing. So here I've got a series of examples that I made, and they're numbered here. So here's number 1, and I'm personally much more comfortable with audio programming than graphics programming. So I just made this work. So we talked before about the idea of a note list. So I decided I wanted a note list that was going to specify what happened to my sine wave. So let me just play it. So there's a 300 hertz sine wave at -6 gain over 500 milliseconds. Here's a 3000 hertz sine wave at -12 gain over 50 milliseconds. Okay, so what happens with this note list? It's a list of 3 floats, and I unpack it. The frequency, even though I come out from right to left, I'm explaining from left to right. The frequency is the easiest. That just goes into the input of the cycle. So this cycle object is continuously making a sine wave at whatever frequency we asked, and we're multiplying it by an amplitude envelope that comes from the line tilde object. The list that sets what happens is of the format a given amplitude that you get to over a certain number of milliseconds, and another amplitude, namely 0, going back to silence, that you get to after another number of milliseconds. What is that number of milliseconds? It's just half of the duration. So we spend half our time going up and then half our time coming back down. So that's why I take the duration divided by 2 and I put it in 2 places in this list. The 0, which is where we end up, never changes. And how loud do we get? Well, it depends on the gain that we ask for. So if the gain is 0, then that's 0 dB, then that's a linear multiplier of 1. So it means we go to 1 over 25 milliseconds. If I ask for -6 dB, then we'd be going to approximately 0.5 over 25 milliseconds. So we half the amplitude. So we make up this list given the gain and the duration. We send it to line so that it makes a 2-segment attack release envelope, and we multiply that by our constantly outputting sine wave from our cycle, and that's the sound of our little blip. So there we go. Here we just quickly, easily make little blips of sound, and we're just using the oscilloscope object to visualize them. But that's just for now. We're going to try to graphically draw the sine wave ourselves, and we'll have much more control over how it looks. So that's number 1. All it does is the sound. So So for the graphics, how do we do this? So here's version 2. It's got all the same stuff on the left, except that I've got the gain that I have going into a scaling thing. So I'm already thinking I'm going to want to control, I want to make the sound and the graphics match each other to a certain extent. So I'm thinking already that whatever gain I use to set the loudness of my audio sine wave blip, I'm also going to use to somehow set the height in pixels of the thing I'm going to make. So that's why I made the scale object. But you see, I haven't connected it to anything yet. I'm just sort of dreaming of how I'm going to connect these to each other. The main thing I've got here is an object called jit.mgraphics, which I found that is for drawing two-dimensional graphics, sort of like a processing object. So if you turn on this Q-metro, then it's outputting a jitter matrix. And you can say, move to the point x equals 10, y equals 100, and draw a line from there to the point 20, 80, and then when you send it stroke, it actually outputs. So if I draw another line to 30, 70, and stroke there, and so on. I guess the stroke takes you back to 0. So there's a reset that clears it. So if we start at 10, 100, and we draw a line from there to 20, 80, and then we draw another line to 30, 70, and we stroke, you can see that I've got two segments here. So that's how I'm going to trace out my sine wave. I'm imagining that I'm going to draw this sine wave as a series of linear segments. And I'm going to use this jit.mgraphics object that is going to be able to make the segments. And also, you can set the line width. So if you clear it and you send those, and the line width is 9, then you've got this fat line. So that's going to be another graphical parameter. We can set the width of the line. Okay, so this is the object we're going to use to draw the graphics. So let's see how I started working on that. So here's version 3, and it's a little bit complicated already. So I've got an origin point. I want to start drawing at some x position and some y position. We'll draw it in the middle of it, and we're going to draw some number of points to the approximation. So let's say we'll use 10 points, which means that it's going to be piecewise linear. So there's going to be one point here and another point here, and we're going to draw a line between them, and a third point with a line, a fourth point, so on. So there's only going to be 10 points. So even though the sine wave curve is in principle totally continuous, and you need infinitely many points to represent it perfectly, we're going to do this kind of low res thing. And we're going to set the height of it to a certain amount, which actually doesn't do anything yet. We're going to set the width to a certain amount, which does do something. And so what's going to happen? Here's the Uzi object that's counting up each point. So in order to draw, the first thing we're going to do is we're going to move to the point that is the origin. So if I'm at x equals 10, y equals 120, let's make something have 0 width, just so you can see that working. So if I click on that, and I turn this on, then you see at x equals 10 pixels in from the left edge of this P window, I got just kind of a vertical line here. And if I made the width be bigger, maybe another 10 pixels, and I banged it, then you see I just get like a random bunch of squiggles. Nothing in the first 10 pixels, and then all this randomness in the next 10 pixels. And how does that work? So Uzi is counting up from 1 to the number of points in my approximation. And when I want to render, first I move to my starting point, the origin, x and y, 10, 120. And you can see as I change that, this POC object is changing the origin point. So let's make our origin be 20 and 100. So first thing that happens is we move to the point 20, 100, and then we're going to bang the Uzi, and it's going to give us, it's going to count through all the points of our approximation, and then for each one, currently we're just going to pick a random y value. So like I said, for now, just make each y pixel be completely random. I don't want to get too confusing at first. This is going to look up the value of the sine function in an appropriate way, but for now, we're not going to do that. We're going to then take this integer, which Uzi is going from 1 to 10, and we're going to scale it so that as you go from 0 to the number of points in the approximation, the output goes between the origin x and the maximum x. What is the maximum x? It's wherever we started plus however wide in pixels we want our little blip to be. So if we want 100 wide, then it's going to look like this. Here, if we clear it. So here are 10 points spaced equally over these 100 pixels. And they're all just random values, but they're taking up a width of 100. Because for each one of these points, Uzi's value goes up by 1, and we scale those values so that when Uzi outputs a 1, we're at the minimum x, and as it climbs, 0 is the minimum x, and that's our starting point here. 1 is the first one in, and that's going to be, well, it's going to be every 10 pixels in this case. So this is counting up, telling us what is the x pixel for each point of the approximation. And then at the end of all that, we send a stroke so that we actually see it. And then one of the important things about this that I like and I want to keep going forward is the ability to draw multiple of these blips into a single jitter matrix. So here's a big wide one. I can also say, let's put another one at a much higher origin with a much narrower width, and draw that. And there's our second one. So I'm already imagining I'm going to fill the screen with a whole bunch of these little sine wave blips that don't yet look like sine waves. So to me, it's important that every time I change the parameters and click on this, it writes more values into this matrix, and I have to manually clear it when I'm done looking at it. Okay, so that's number 3. So it's the whole mechanism of counting up through however many points I have in my approximation, knowing the x coordinate of each of those points, and then computing a y value, which in this case, again, is just coming from this random object. Okay, so let's make it be correct. Let's make it actually draw the sine wave. So this mechanism is all very much the same as what we saw. The only difference is down here. Now, instead of just banging this random, I'm sending an integer into here. That is, which point are we in the approximation? And I'm using another scale object that's taking the range of integers that Uzi is outputting from 0 to the number of points in my approximation and scaling it to go from 0 to some higher value, namely, how many periods of the wave that I want to draw. So it turns out that the input has to increase by 2 pi to go through one cycle of the sine wave. So that's what this is. 6.2832 is 2 times pi. And how many periods I want to draw, I multiply it by that. And now, as my input goes from 0 to 40, I'm scaling it so that it goes from 0 to 2 times 2 pi. And I take a sine of each of those values, and that gives me a number between -1 and 1. And I'm just going to vertically scale it to go between 180 and 60. So it's going to look like this. Boom. So there's exactly 2 cycles of my sine wave with a 40-point approximation. Also notice I added a bunch of load messes. There's so many parameters that you have to set in order to get this thing to even do anything. I added these load messes that make the thing happen. So that's 200 pixel wide thing. So let's make another one that starts further to the right of the screen, and that's narrower in pixels, and that draws 3 periods. And so there we are, further to the right, 1, 2, 3 periods that go up and down. And it doesn't have to be an integer. We could clear it. We could have it draw 3.5 periods. And now you can see it goes up and down 3 times and then up, well, up and down and back up. There's 3.5 cycles of the waveform here. Take my word for it. Okay, so now we're actually rendering little bits of sine wave, so that's exciting. This patch, however, it's getting a little bit messy. It's a little bit hard to follow what's happening. But we're going to make it even slightly worse. Now we're going to actually scale it correctly. So before, again, in this one, all of my sine waves, no matter how big I made them, like I said, for now, don't think about vertical scaling. Make it always be in the middle half of the window between y equals 60 and y equals 180. So we're getting rid of that. Now we're going to make it so that I can set the height in pixels. Here's defaulting to 100 because of this load mass. And what am I doing with that? 100. It's going into here. It's going into 0.5 because however tall the thing is, it means whatever my starting Y value is. If the thing is 100 pixels high, then I want to go from my starting value plus 50 to my starting value minus 50. So I'm taking my desired height, I'm multiplying it by half, and then I'm adding it and subtracting it from my starting Y position, here 120. And that is going to scale my sine wave. So let me show that working. So here's my 2-period sine wave starting at x equals 20, y equals 120 with a height of 100 pixels, 101 pixels. And now let's do the same thing with a height of only 10 pixels. And you see a much lower amplitude sine wave starting and ending at the same points, but not excursioning as much as the other one. So all of this mechanism, I think, is correctly drawing the sine wave the way I like it. So that's version 5 of this patch. Okay, so now my thought is there's a lot of stuff in here. I don't want to think about all these details. So my first thing I'm going to try to do is make an abstraction. So an encapsulation. Before we get to an abstraction, I'm going to make a subpatch. So the way I did that is I took all this stuff and I said, okay, what's in and what's out? So this audio stuff, that's out. I want to leave that alone. The actual window that I'm looking at, that's out. I want to leave that alone. And now I'm going to select all this stuff and I'm going to decide that the height in pixels is out. Meaning it's not part of the abstraction, it's part of how I want to control the abstraction. The number of points in the approximation, this is a parameter that I'm setting, and so on. So I select a bunch of stuff, I deselect a bunch of stuff. My point in doing all this is I'm making a distinction in my mind between the part that actually draws the sine wave and the part that figures out how the sine wave should look. So having done all this, I say encapsulate, and it puts it all inside this subpatcher, and it leaves as many inlets as I need to connect all the things into it, and it leaves an outlet so that thing can come out. So basically that's what I did in this case, number 6.whoops, except I missed this object, this button that's triggering the whole thing. So you see there's a lot of inlets to this subpatcher, and I don't like the fact that the sequence of do this first, then this second, then this third is outside of the patcher. This TBBB doesn't really mean anything to me without seeing what it connects to. So here's my subpatcher, and it's all the same stuff we were looking at, except now it has a bunch of inlets. But this is, I call this whoops because this is indicative of the kind of error that you can make when you're trying to encapsulate something, but you choose wrongly. So in my opinion, this trigger should have gone inside, which is why I did it again. In a slightly more careful way. So I'm making an even worse mess temporarily because it's going to get clean and nice. So what I did is I determined for myself what are the things that are outside and what are the things that are inside. So this is the button that makes it all happen. And I made that connect to this button and the trigger that we had before. This is the number of points in the approximation. Inside the patcher, I want to see that, but also it's something I want to be able to set from outside the patcher. So I duplicated this thing as a parameter so that I would have a version that's going to be outside my subpatcher and all this stuff is going to be inside my subpatcher. So having very carefully separated all my parameters and made copies of it and so on like that, then now when I say encapsulate, then it does that. And indeed, that is what we have in this next version, .encapsulated. Okay, so now I have a subpatcher, still not an abstraction, subpatcher called draw sine squiggle that does everything we just learned. I haven't changed the behavior of the program at all. I'm just changing the way that it's organized in terms of subpatches. So now outside of it, all I have are things that set the parameters. So this is the kind of way of thinking that leads to abstractions. This idea that if I'm trying to make it work, I have to understand all this stuff. But once I got it working, I can just kind of put it on a box and close that box and just use it. I can just say, hey, give me a sine wave. Okay, now change the parameters. Give me another sine wave, and it works. And so this is now turning into what's often called metaphorically a black box, meaning a piece of a program that has a certain behavior that you don't have to know how the insides work. You just use it from the outside. So here we are. It's a subpatcher called draw sine squiggle, and it does exactly what we want. We can keep drawing over and over again. I guess it will maybe get darker and darker. I'm not sure why it's overwriting that stroke. It's kind of a cool effect. I might want to use that later. Okay, so there's encapsulation giving me a way to not have to think about all the details of drawing. So now I can look at this patch and say, okay, well, it's a little bit complicated the way that you actually draw the sine squiggle. And if you want to know how it works, you can double click it and you can look at all this programming inside. But if you say, okay, I trust that it works, I believe it. Now I just want to be an artist and make up some numbers and draw those. You can do that too. In other words, using this object rather than implementing it. Okay, so that's my version 8 that encapsulates. So one of the problems with this encapsulated version, I can add lots of things. I can make multiple sine waves. I can put them in there. But what happened to my clear message? I forgot to leave that outside. And there's actually this whole subpatcher that I took from the help patch of jit.mgraphics that does a whole bunch of stuff to make it reset. And I can go into the inside and click to make it clear. But obviously I don't want to do that. I want to have the ability to clear it, be something that's exposed to the outside. So again, I'm in my mind, I'm making a distinction between how I want to think as a user of this object versus how I want to think as the implementer of this object. So as a user of this object, I want to just be able to say clear, not clear color, but just plain clear, and send it into the object and have it clear. Currently it doesn't. Currently it does whatever it does, but the next version does. So that's what this version 9 does. It takes a clear message. So here's my thing. If I send it to clear, it clears. And here inside, on the first inlet, I put a route object. So that if the message clear comes in, then it sends a bang into that reset and it clears. And otherwise, it gets it to trigger the rendering of one of these sine waves. So now I can draw sine waves, I can change the parameters of those sine waves, and I can clear, and it works. So there's a clear message that can go into here. So that makes me think, well, why do I want all these different arguments? All of these inlets. How many inlets are here? There's the one that makes it actually do something, and then 1, 2, 3, 4, 5, 6 that are the 6 parameters of telling it how I want that little sine wave to look. So I'm thinking that instead of having 6 inlets, here, total of 7, the one that makes it do stuff plus the 6 to set the parameters, I want to just like have a note list over here. I want to have a squiggle list over here. So I'm using a POC object, and I'm making it be that whenever I change the parameters, these now 6 parameters that determine what my squiggle is going to look like, I'm just going to put them together in a list that says squiggle. Now this list doesn't do anything yet, but in this next version I'm going to show you right now, we're going to move towards that. So AV science, now we're up to number 10 of this series. So I'm making the squiggle message, and now I'm actually connecting the squiggle message to it. And so far I'm not doing anything with that squiggle message. I'm getting it, and I'm just sending it into this unpack. So the squiggle message comes in the left, and I'm going to take that list, and I'm putting it in this message box here just so that I can read it, and I made an unpack, and I put a comment there, so I'm labeling what these 6 elements of the squiggle message mean to me. And right now all I'm doing is I'm taking the number of points in the approximation and connecting it to the appropriate number box. So this is a squiggle that ends in 40, and so that's at the 40 here. If I change the number of points to 117, then here's the 117 here. But this is only part way. I haven't actually finished doing it. I just started connecting the squiggle message. Obviously all the other parameters in the squiggle message aren't doing anything yet, but I just want to have that be separate. So here's the final version, squiggle message.2. So first thing, notice there's now only a single inlet on my draw sine squiggle patcher. And here's a message that says squiggle this, and if we change the parameters of the squiggle, I'm just kind of being pretty random about this, and draw it again, we get another sine wave because this squiggle message makes that sine wave. And a nice feature about this is that now I can option click and drag on this, and if I find some parameters that I really like, not that these are that great, but just showing the idea of randomly changing it. Okay, that one's too low, it's off the screen, so let's make the y value be a little bit lower. That's still too much. The height is too big. We'll clear. Okay, that's a squiggle I can get behind. Wait, but I want more periods in there. That's a good squiggle. So here is another squiggle that I like. So now I'm saving. I have these messages that correspond to squiggles that I like. So now I can recall them directly with this. So that's kind of cool. But that's just kind of a side effect of the way that I'm using message boxes here. Let's look inside here and see what's really happening. So what I did is I got rid of all the inlets and I replaced them with this unpack. So now the origin x comes from the squiggle message through this unpack object and it goes to where the origin x used to be, the origin y, the width, the height. All these 6 parameters are going to the right places. Also, in the previous version, I had a bunch of tbf objects inside here because I didn't know whether I was going to change the height and then change the origin y, or if I was going to change the origin y and then change the height. So I needed this tbf right here so that either way, it was like both inlets hot on the plus object. But now I don't need that anymore because I know that there's going to be exactly one squiggle per list, and I know that unpack is going to output from right to left. So I know for sure that the width is going to come first and the origin x is going to come second. So I don't have to worry about, well, what happens if I change the width without also changing the x? I know that that can happen because all these 6 numbers are always going to come out 1, 2, 3, 4, 5, 6 in order from this unpack. So that simplified the patch a little bit more. So this is basically how I want it. This is my sine wave squiggle. And notice this development style that I made it first. First, I didn't know what I was doing at all. I was just messing around. I was just prototyping. I was seeing whether I could get it to do what I wanted. It was messy. I was experimenting. I didn't know it was important. I was just kind of making a mess. And then I said, okay, this part is going to be useful. So I'm going to make a subpatch out of that. And then I was adjusting. I was like, how do I want to control that? I want a clear message. I don't want all these separate inputs, inlets. I just want a single message that I can send it that's going to have the 6 parameters in it. So I've adjusted it, now to the point where I think that this draw sine squiggle is something that I'm going to be able to use repeatedly. And so now I'm going to make an abstraction out of it. So here's my draw sine squiggle. It's actually bigger than the screen here, so I got to make the thing a little bit smaller so I can get down here. I'm going to open it up here. And again, just like I showed in my simple example, I'm going to do a save as. So this is a subpatcher. And I'm going to save it. It's defaulting to the place that I saved before, my max path folder, which is a good place for it. And draw sine squiggle is also a good name for it. So I'm going to do that. Draw sine squiggle.maxpath. So now it's going to be there. So if I look in my documents, here's my max path, and there's this patch that was just created, draw sine squiggle.maxpath. And now if I open a new patch and I say draw, again, it's giving me command completion suggesting that I want to draw a sine squiggle object. And there it is. And here's an example of a squiggle message. So I'll just copy that in there. And I'll make a jit.p window. And there's my squiggle. Okay, so now I've got this object that does what I want, and I can make multiple versions of it. I'm not sure yet how I'm going to use multiple versions of it because I can just send multiple messages to it and it'll draw multiple squiggles, but that could come in handy. So as you know, subpatchers are stored inside the patcher that encloses them. So here I am with my draw sine squiggle, and I'm all ready to make into an abstraction. I'll just make a little meaningless modification, move something around. You see that this little red circle here is filled in to show me that the things are modified, and also the enclosing patch, this number 11 in our series, also has been modified since it was last saved. If I just say save at this point, even though I have my subpatcher draw sine squiggle selected, if I say save, then what got saved is the outer enclosing patch, because that's where draw sine squiggle gets saved as part of AD sine 11, blah, 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 blah. So if I want to turn this draw sine squiggle into an abstraction, I can't just say save, I have to say save as. So that's why my normal technique of starting something as a subpatcher and then graduating it to an abstraction once it's ready involves this save as step. So I did that already, and I made a thing called draw sine squiggle.1.maxpath, which is exactly what you just saw here. I put a .1 on it thinking that there might be a series of these, and that I might, since I'm showing you this in sort of historical progression, I might make a .2 at some point in the future. So that's why that .1 is there. You can ignore that if you don't like it. So now I made an abstraction. Here's number 12 in our series. It just uses the abstractions. This is exactly the same, except right here, instead of a subpatcher, I'm calling out to draw sine squiggle.1, and there you go. I can draw squiggle just like all the ones that we've seen so far. So that's number 12. The only thing I changed is instead of being a subpatcher, it's an abstraction. So now if I were to change the abstraction, let's say I go into draw sine squiggle and I default the line width to be a little bit bigger. Let's make it default 2. Whoops, I missed again. Let's see if I can do this right. There we go. So now line width is 2. So if I save this and I draw my squiggle again, now it's thicker. So this is the behavior I was talking about, where if you change an abstraction, then all the programs that refer to the abstraction inherit the new behavior. So there's my now twice as wide line width sine squiggle. So far, I had sort of started to draw these connections in number 12 that say, well, if the thing's duration, the duration of the sound that I make, if here this one is 800 milliseconds long, that should somehow scale to give me a width in pixels, here 52. And if it were a longer one like this, well, here's a short one, 50 milliseconds, so that's going to make something that's only 4 pixels wide. So there's a little very tiny one. It's also short in height because I've got the gain controlling the height and the duration controlling width. So let's take that a little bit further. So what I did is I took all the stuff about computing the graphical look of the squiggle, and I just moved it down a little bit so that these patch cords where the parameters are controlling the audio are controlling the graphics are a little bit further down. And I added another one. I added this little mechanism so that every time I draw the next thing, I move it over 10 pixels. So this counter is going from 1 to 25. So the first thing I draw is going to be at origin 10, and then the next thing I draw will be origin 20, 30, 40, 50, 60, 70, 80, until I get off the end of the screen. And I better change some of these parameters here. We'll make it taller. So this next one's going to be the last one at 250, and then this counter wraps around and we start over 10. So this way I'm just kind of gradually moving my way across the screen every time I draw with this counter. And the height, if I clear this, this is a loud one, so it's tall. This is a quiet one, so it's short. And it's also a short duration one, so it's skinny, whereas this one that's longer duration is wider. So that's just sort of the beginning of doing that. And I'm really not liking the messiness of all these overlapping patch cords. So this is a case where the sort of visual aesthetics of the max patch are giving you a clue as to the clarity of the thinking that went into it. So this is a messy looking patch, and it's making me think that maybe the way that I'm doing this is not going to be an efficient way for me to think about it. So I'm going to start cleaning it up. So first thing I'm going to do is, instead of pulling data out of the internals of this audio processing part where I've unpacked it and I figured out the gain, I've converted it from dB to A and so on, I'm just going to take the same note list and pass it over here. So I'm keeping this separate. I'm going to pass the note list into the audio stuff that's self-contained on this side. I'm going to pass the same note list over on this side. And I'm going to do another unpack. I just copied all this stuff. Again, option click and drag will copy a selection. I copied that over there, and I connected that up. And then I just kind of changed this around a little bit. So it used to be coming out of here, so I was using the linear amplitude, but I figure I'm not trying to perfectly graph exactly the true function of everything. I just want them to be somewhat subjectively related to each other. So I'm recomputing the height as a function of the gain in dB, so that negative 20 dB is 0 height, and 0 dB is full amplitude is 200 pixels tall. So you can see as I change the gain here, this height in pixels is changing correspondingly. So now these are independent, it's not crossing so much. I still don't really like the way these are crossing, so this next one, the next cleanup, I traded them crossing down here for them crossing up there, so I'm not sure that that's much better. The other thing I did is I took all the stuff that was making my sine blip and I encapsulated it. I decided that I want to keep the audio separate, and this is a nice sort of self-contained, easy to understand thing on its own, so I just made a subpatcher for it. So now I have a patcher sine blip, and this works as before. except now every time I synthesize a new audio blip, it also renders a new little graphical squiggle. So that's good. So let's clean up too. What's my next step of cleaning this up? I just made a whole subpatcher for the graphics. So comparison, I took all this stuff that was computing the parameters of the squiggle. I've already made an abstraction that takes this list, this squiggle list, we'll call it by analogy no list, and does everything to make the commands to actually do the drawing with JIT.engraphics. But now I've taken all the stuff that sets the parameters of that and encapsulated it in a patcher called graphics. So now this is looking very clear and easy to look at, and it still works the same. I can still clear it. And I also added a feature that when I clear, that's this left inlet here, I not only, sorry, this right inlet number 2, when I clear, I not only send a message down, I don't not only send the message to draw a sign squiggle, but I also reset the counter, so that if I've drawn a bunch of things, and I clear, then I'm gonna start over at the left edge of the patch. So that's cleanup number 3, and I kinda like this. There's this audio on this side, the graphics on this side, the control, the sort of compositional parameters are still these 3 same message box presets I started with. So let's take a look at that next. So this next version, .17, I labeled generative. So now instead of just clicking on these 3 message boxes as I've been doing, first of all, let me zoom back out. So you see it looks exactly the same down here. I got the same sign blip patcher, I got the same graphics patcher, all this stuff is the same, but now I want to make up more of these things, and I'm going to do it in a quasi-generative fashion. So for the gain in dB, I'm just going to pick a random number between 0 and 19, and I'm going to subtract it from 0, so I get a random number between 0 and -19. So every time I want a new note, I'll just pick an amplitude randomly. And what about the frequencies? I don't want to just pick random frequencies. I want to decide what frequencies I'm going to use. So I typed in all these frequencies into this message box, and I built this little thing that picks a random element from the list. So here's my list. I put it in ZLN. It tells me that there are 12 elements in this list. So that sets the range of the random numbers to be from 0 to 11. So now every time I bang, it's going to pick a number between 0 and 11. And then I'm going to take that number and pass it into ZLmth. Remember, mth is 1 origin, mth is 0 origin, and since random goes between 0 and the number -1, it's sort of already a 0 origin thing, so that's why I'm using mth instead of nth. And every time I pick a number such as 8, I put it into the cold right inlet of ZLmth, so it knows it's picking the 8th element of this list, and then I send it bang, so that it will go 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4 is the 8th element of this list, 0 origin, and so that's giving my frequency. So now I'm going to pick a random frequency, but drawn from this list. Okay, so every note is drawn from the scale I typed in. So let me give it a really simple example, 200, 300, 400. So if this were the list of frequencies, then there would only be 3 possibilities. So you can hear I'm only getting those 3 notes, but I like those better. So that's the beginning of the generative. Now what about the duration? I haven't done anything with that yet, so far all these are 200 milliseconds. I realize I want to use this exact same mechanism. I just want to type in a list of the allowable durations for notes. I want to pick a random one. So rather than duplicating all of this mechanism that picks a random element from a list, I don't want to make 2 copies of all that. I want to use an abstraction. So I made an abstraction called random list element, which I did using the same sort of encapsulate save as mechanism. So now there's some arbitrary list that comes in the right. I gave ZLmth the argument -1 because the left inlet is hot, and when I first initialize this, I don't want it to send out one of the values of the list. I want it to wait until I'm actually sending a bang to pick an element of the list. So that -1 says that I'm defaulting to giving an element that isn't even in the list, so that makes it not output anything. So this is kind of a way of preventing an output when I set the list. I only want it to output when I send it a bang, and it picks a random element of the list. So that's random list element, and now having done that, I have number 18, pick durations too. So here's one random list element that is picking the frequency, and now here's another random list element that is picking the duration. So here's a list of durations that I made up, and every time I send this thing a bang, it's going to randomly choose one from this list. So here's a great example of using an abstraction. I've got a task that's very well defined, that is very general. Just pick a random element from a list. Could be a list of durations, could be a list of pitches, could be a list of things that I am not even thinking of when I write the object, but I can write the object. It's a generally useful thing. It's got inlets, it's got an outlet, it does its job, and then when I need another object that does that same job, I just make another copy of random list element. And if I found some bug in here, I could go in here and change it. Then all of these instances of it would inherit the updated behavior, and it works. So that's a good style of programming. So here I'll turn my gain up, and I'll clear, and here's some music. Okay, so maybe not the most thrilling music, and I'm not that thrilled about having to click this button every time a new note comes out. That could be a good thing. I might want to incorporate this into some live process. Maybe I want to be typing like a letter to my friend, and every time I press a key, it plays the next note. We can do that very easily, right? We just put a key object here, and we don't even care what key it is. We'll just connect it to the button, so now I can just type. But I don't think I want to go in that direction. I want to make it do it on its own. So that's why I made this next version called sequencing. Okay, so now when I pick the duration, I'm going to do 2 things with it. I'm going to use it to set the duration of the sign blip that I'm going to synthesize, but I'm also going to take that same number of milliseconds, that's the duration, and set a delay object to wait that amount of time, and then send a bang in, so that if the duration of this note is 400, then we'll make a, well here, this one was 2200. So it makes a sound that's 2200 milliseconds long, and then also this delay gets asked to output a bang in 2200 milliseconds, and then that bang goes around back into this gate. Whenever you have one of these kind of feedback loops where doing something causes the next thing to happen, then that's going to go infinitely, so that's why I put a gate in here so I can break it. So if I open the gate, and I start things off, then now it's playing by itself. So every time a note comes out, after the end of that note, the next note comes. So this will go by itself infinitely until I click on this and turn off the gate. Okay, so this is what you would call monophonic, meaning that there's only one pitch happening at a time. There's only one note sounding. So if the note lasts for 300 milliseconds, the next note, not only does the note stop after 300 milliseconds, but the next note starts after 300 milliseconds. So what if I want to, first of all, what if I want some space in my music? What if I want to play a short note and then wait some amount of time before the next note starts? Or the other way around, what if I want to play a long note and before that note is over, play the next note? So that's this idea of overlapping notes. So that's this number 20 right here. Here's the first idea. I'll take my list of possible durations and I'll pass them into 2 different random list element objects. And one of them will choose the duration of the note, how long it'll sound, how long between when the note starts and when the note stops, as we've been doing before. But then this other one will set the amount of time before the next note begins. So what happens when I do this? I have to open the gate to let the thing do its job. What I'm hearing and what I can actually see on some of these notes right here is behavior that I could have easily predicted because I only have one sine wave. So this object, if it's in the middle of this ramp and it's slowly fading in and fading out, and then before it gets to the end, it gets asked to do something else, well, it's just going to jump to the next thing. It's going to forget the end of the note it was trying to play. The cycle will immediately change frequency, and the line, even though it wasn't at 0, will change. So you can see, here, let me stop audio right when something like that happens. Well, you can You can see from looking at this, and you can hear that there aren't overlapping notes. There's just notes that didn't get to finish and got interrupted. So the only way to have overlapping notes, while they're overlapping, we have to hear two sine waves at the same time. So this sine blip, these are some synthesis resources. This oscillator, the cycle object, and the lying tail object that's making the amplitude envelope. I need multiple copies of this. I need one to be playing the old note, and then the next one to play the new note. So that's what this next version is. .21, the conclusion of this long story about the audiovisual sine wave sequencer. I made polyphony. I made 5 instances of sine blip. Okay, so first of all, how did I do that? I took my subpatcher, and I did a save as. So I made an abstraction called sine blip, which is exactly the same as what had been the subpatcher. But having done that, I was then able to make 5 of them. So I just plopped 5 down right here. And I'm using, again, the round robin scheduling algorithm. So I've got this counter that's going 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and I'm sticking that number onto the front of my note list. And I'm putting it through this object spray that looks at, it's kind of like, in fact, in this case, it's exactly like if I just said route 1, 2, 3, 4, 5. So if a list begins with 1, then the rest of that list comes out the left. If a list begins with 2, the rest of that list comes out the second outlet, etc. So I stick the voice number on the front of the note list so that spray can use it to send each note in turn to the next synth. So if I play 10 really long notes really fast, I only have 5 voices of polyphony, so I'm going to still have this property where I'm interrupting a note where it doesn't get a chance to fully finish. But now that I have 5, I sort of have enough of a buffer that at the rates that I'm using this, it's working. So here's the punchline. I'll turn on sound. I'll open the gate. That's a nice little opening flourish there. So you heard a bunch of notes at the same time. Okay, so if you don't like all these crazy durations that give you this kind of arrhythmic or strangely rhythmic music, let's just set them. So we only have 3 possible durations. So that's got a little bit more of a steady beat. In the extreme case, I can just make it have only 2 durations. Well, I guess only 1 duration. What does that sound like? Should be exactly the same now. Now it's just on a metronome, 3 notes per second. And I could use different lists for the 2. So I could be going, each note could last 333, but I could make the time between notes either 100 or 200. So there's a lot of possibilities here. This is kind of a rich thing. Another thing I might want to add, this thing just kind of keeps getting fuller and fuller and fuller and fuller. Eventually it's just kind of a big black blob. So first of all, that makes me want to change the pen width back to 1. So I'll do that. I'll save that patch. And now, look, we instantly inherited that behavior. That's pretty cool. So maybe I want to think that every so often we'll clear it. Or who knows? So I think you get the idea of abstractions. We started from nothing and we made something that is arguably somewhat interesting here. So I'm gonna leave it here, and maybe you'll think of some future directions that you want to take this, and maybe you can modify this into something that is even more personally thrilling for you. I'm going to briefly review the complete rules of Max. This is some of the deepest knowledge in the class. So let's succinctly restate Max's evaluation rules, the step-by-step logic of the Max interpreter. So Max programs consist of objects and and connections between those objects. So that forms a directed graph because a connection goes from an outlet to an inlet. And in Max, these graphs can be cyclic. So there can be cycles where you've got some objects and they output something, and the outputs go around back to the top and back in to other inlets of other objects. So without the proper insertion of some kind of delay or using a cold inlet or using a set message to send something to an object in a way that makes it not output, then this loop can turn into an infinite loop, which can lead to a stack overflow, as we saw. So I think it's important to be able to understand Max as an ecosystem in which each independent object can send messages to each other and schedule according to a common time base. So Max brings all these objects together in a certain way, but it also gives them their independence in a certain way. As you recall, there are about 600, a little more than 600 objects built into Max. Very important aspect of this ecosystem and the way that objects communicate with each other is that, with a few exceptions, they don't care about anything except what comes into their outlets. I'm anthropomorphizing them a little bit, saying that they care or know certain things, and you shouldn't anthropomorphize computers because they hate that. But let's just imagine that each object has a personality, and the personality of the object is oblivious to the whole rest of the patch. If a number comes in, doesn't matter where that came from, doesn't matter who produced that number, doesn't matter how much processing went into that number. By the time the number gets to the object, it's just a number like any other number, and the object does what it's going to do with the number. So very common mistake that beginners make with Max is they somehow think that there's some context that goes along with the number, that the number somehow remembers where it came from or something like this. But no, once it's a number that goes into an inlet, it's just a piece of data that's stripped of all other information. For the most part, an object's view of the world does not extend beyond incoming messages, and the effect of an object on the world does not extend beyond the messages that it outputs. So we learned that the way that message connections work, when an object outputs a message, there's a function call that happens underneath the scenes, and that means a stack frame that gets created. So we've talked about this stack-based model of understanding how the Max interpreter will deal with a chain of connections. So that an object outputs something, and that goes to another object that outputs something, and so on. We've talked about that in terms of depth-first traversal of a patch. We talked about Max's right-to-left rules, that if an output of an object, if an outlet is connected to multiple objects in the patch, then by default it's going to go first to the rightmost one, then to the next, then to the next, all the way to the left. And we talked about how it can be dangerous to rely upon that behavior, and if you need something to happen in a specific sequence, then I recommend using the trigger object, which also outputs from right to left, but in a controlled way, with each outlet being individual. We also talked about hot and cold inlets. So remember, if your mouse over an object's inlet while it's the patch is in edit mode, you see that a red inlet is hot, meaning when something comes in that inlet, the object is going to output, whereas a cold inlet, something goes in that inlet and the object remembers it but doesn't output anything. Another hugely important part of Max is the scheduler, which is what allows things to happen in the future. So we've looked at several objects that take advantage of the scheduler, such as metro, delay, pipe, make note. All these objects do their job by making something happen, possibly making something happen now, but arranging for something to happen some amount of time in the future. And that all goes through the Max scheduler. So there are a few exceptions, as I mentioned. So there are several objects that communicate with the rest of the world other than through inlets and outlets. Some examples of this are the key and key up objects that they don't have inlets, they take data from a keyboard. Likewise, the mouse state object doesn't have any, it doesn't need an inlet because it's taking data from the mouse. All the MIDI objects are taking, well, the MIDI in objects are taking in data that arrives in MIDI. The MIDI out objects are outputting data to MIDI. The ADC and DAC objects for audio I/O, they work by talking to the outside world. They're objects that save and load files. There's also the send and receive pair of objects that we saw in the last session that allow connection through a named channel rather than an explicit patch cord. So we talked about a directed graph where an object's outlets have data flowing out of them into inlets of other objects. So Max has a couple of exceptions to this where the data, I would say, flows backwards up an object. So let me show you a couple of those. There's an object called grab. We can send a message into this plus object via the grab object, and the grab will intercept the output that this object would have used. Typically, if you send the 5 into this object, the output comes out its outlet, and you see the 8. But if you send the 5, well, now let's make it the 6, into the grab object, nothing comes out the plus object. So this grab object is there to sort of steal, to get an object to do its bidding, but then to steal the output. I typically use this when I have a collection and I want to know the length of the collection. And again, the whole point of grab is to subvert the normal rule of Max and to, as I think of it, suck data out an inlet. So that's this connection right here is a little bit bizarre. It breaks the rules. There's also, we talked about attributes for objects. So for example, there's an object called make note, and if I control click on its input, we see it has an attribute for the duration of the object. And if I select that, then I get a object of the type, this object is called attrui, attribute user interface. There are two attributes of make note. There's duration and repeat mode, and duration is the number of milliseconds, and you can change the duration just by typing into this object. And if you set the duration of the object with another mechanism, like if you send it the message duration 555, then this attrui object very conveniently updates. So if the outlet of this object is going into the inlet of another object, then not only can you use this object to change the value of the attribute, but if something else changes that attribute, then the information about the changed attribute, again, it flows backwards up this patch cord into the attrui object, so that what it's displaying is always the true current value of that attribute, whether you set it through this object or through some other mechanism. So that's the attrui object. Oh, another example that we saw is the preset object, where you connect it to certain objects in your patch, like say a couple of message boxes, and you can set some values in them, let's say 1 in both of these, and you can shift click to record it. You can set some other value and shift click to record that. So when I'm recording the values of these objects, again, this is a sort of backwards patch table. The data from these objects is being sucked backwards through the patch table, so that when I recall a preset, it's kind of working in the normal way, where the data is coming out of the preset into the number boxes. But when I save a preset, the data is going backwards through the patch tables. We're also going to talk a little bit today about the patcher system, patcher attribute, PATTR, that works like that. Another exception, another example of data flowing backwards through patch cord is an object called playbar. So let me introduce that. So normally we've been playing movies using the very convenient jit.movie object, where you can, as you've seen many times, you can connect the output of the object into a jit.p window and play it and stop it and set it to loop or not to loop or whatever. There's actually a much more flexible object called jit.movie that can do all kinds of stuff. Let's steal some stuff from the help patch here. So you can read a movie from a file, you can start it playing, you can stop it playing. Here's an example of a playbar. In fact, maybe I'll just put this whole example in here. So we can read a movie, and conveniently I have chickens.mp4 on my desktop. Here's our chickens going, and we can stop it, and we can start it again. Another thing you can do is you can go to a specific frame of the movie. So you can say, I want you to be on frame 5, go. And it jumps back to frame 5. Or you can like zoom through the movie backwards and forwards, however you like. So notice this playbar object, I can pause the movie, I can start it, I can scrub forwards and backwards in time through the movie. So this playbar object can control what's happening in the movie. But also if I use some other mechanism to go to another part of the movie, like stopping it, starting it, jumping to a new frame, etc., this playbar object is updating its graphical state. So like with adder UI, you want it to not only control the movie object, but if something else controls the movie object, you want the visual state of this object to reflect what's happening. So again, this is another exception to the rule that data always flows from an outlet to an inlet, because here if I stop the movie, then the fact that the movie stopped went backwards from the movie into the playbar object. Playbar also works with the sfplay tilde object for playing sound files. Incidentally, Max has at least 4 ways of playing a movie. Most of them work with playbar. So this is what we've been using for the most part. Jit.playlist. Here's an object jit.movie that reads in a movie from disk, and you play it by spitting out each frame as a jitter matrix. There's also an object called justPlayMovie in Max that, again, you can read in a movie, and it, if you double-click it, it opens a whole separate window. So it plays the movie into a totally different window. Useful, perhaps, if you're VJing or something, and you want to you want to be able to move this over on another screen that is on the projector. And then finally, there's iMovie, which is sort of like jit.p window, where it displays the movie right directly in your patch I for a user interface object. And again, we're looking at a high-res version of the upper left-hand corner of this movie. I'm sure there's a way to downsample the movie. So all of these ways of using a movie, except for jit.playlist, can be controlled with playbar. And again, the point of all this is to just give you a few examples of the exceptions to the rule that data flows out of outlets into inlets. MSP is the signal processing part of Max, and although it was originally a separate product, it's now fully integrated into Max. So you may hear people say Max MSP, but there's not really any difference between Max and MSP anymore. You can't get Max without MSP these days. But MSP is a separate ecosystem, again, where independent objects communicate through a defined channel, in this case, signals. So unlike events, which happen from time to time asynchronously, signals happen synchronously. They're going continuously. As long as audio is on, all the signal objects are processing all their inputs and outputs and reading signals and writing signals. So what is a signal? It's a stream of floating point numbers that represent samples of a digitally sampled signal, and the rate of those samples is what's called the sampling rate. It's typically something like 44,100 samples per second, or 48,000 samples per second, or 92,000 samples per second. Typically people say K, so 92K meaning 92,000 samples per second. For sampling rate, you're just counting the number of samples, you can say 92K samples, but usually people are counting the number of samples per second. If you're talking about the duration of something, you would often talk in terms of some other unit of time, like milliseconds or whatever. So that's how tightly you are sampling the world along the time axis. How tightly you're sampling the world along the amplitude axis is the bit depth. So that is a function of the hardware that you're using with Max, whether you have 16-bit converters or 24-bit converters or whatever. All those differences kind of get glossed over in Max because Max represents samples as floating point numbers. So it's not a fixed number of bits like the integer samples that are actually going back and forth to the audio hardware, but those integers, every single sample gets converted from an integer to a float when we're talking about an audio input going into Max through the ADC object. And likewise, when you write values out of Max using the DAC object, writing signals, outputting signals from Max, your program is computing 32-bit floating point numbers, but when Max actually outputs it to the hardware, it looks to see how many bits of depth your hardware has, and it converts from floating point number to the appropriate size integer. Here's a new point that we haven't talked about yet, we managed to gloss over. Signal processing does not happen one sample at a time in Max. You might think that 44,100 times a second, every single object reads in its next one input sample and outputs its next one output sample, but actually it's much more efficient to process audio signals in blocks. It's called block-based processing. In Max it's called vectors. So let's take a look at the audio status window. And we see this setting here as to whether audio is turned on or off, and it's telling you which audio driver we're using, which input and output we use. Here's the sampling rate. Again, there's the two common ones that you see most often. And then here, this next number is the I/O vector size, input-output vector size. This is the number of samples at a time that Max communicates back and forth to the audio hardware. So right now, I'm just using a built-in audio hardware on this laptop. So Max is talking to the operating system every 64 samples and getting the next 64 input samples if I'm using an audio input, and writing out the next 64 output samples if I'm producing an audio output. And we can set that to any power of 2, in this case between 32 and 2048. Different audio hardware supports different signal vector sizes. Sometimes you can go down even to as low as 2 samples in the audio vector size. How do you choose this number? Well, it's basically a trade-off between efficiency and low latency. So in order for Max to receive 64 samples from the audio hardware, enough time has to pass, a little bit over a millisecond, that the audio hardware can gather up these 64 samples. So they're coming in one at a time, 44,100 times a second, and after a little over a millisecond, this buffer is filled up, and boom, the hardware has 64 samples, so it sends them to Max. Maybe there's multiple input channels, so if there's, in this case, stereo input, that's 64 samples for the left and 64 samples for the right. If you're doing some huge, multi-microphone type thing, and you're using a big external audio device that has, 16 inputs or whatever, then you get 64 samples for each of those input signals. So those all go to Max. Max gets a message, MSP gets a message from the hardware that says, hey, here's some new input audio for you. Here's a bunch of new signals, a new audio I/O vectors worth of signals. Here's all the inputs. So MSP goes through its whole routine, which I'll summarize in a moment, and it produces at the end of the day all the outputs that are going to all of the D to A converter channels. And again, there might be only 2, or there might be a larger number depending on what audio hardware Max is plugged into. And in between, all the signal processing happens. Now, the signal processing actually happens also in blocks, and typically, and that block size is determined by the signal vector size. So the I/O vector size is how many samples at a time the hardware communicates with MSP to say, here are some new input samples, please give me the same number of output samples. The signal vector size is how many samples at a time MSP processes. So if you set this I/O vector size to 256, and you leave the signal vector size at 64, then every 256 samples, MSP gets woken up and given the new input samples and asked to compute the new output samples. And MSP will do it by first doing the first 64, then the next 64, then the next 64, then the last 64. So it can process them in sort of 4 blocks of 64, or 8 blocks of 16, or 2 blocks of 128, or all in 1 block of 256. For most applications, you want to have the signal vector size equal to the I/O vector size. And I started talking about latency so it takes time to gather up these 64 samples, and it takes twice as long, or 4 times as long, or 8 times as long. So with 2048 I/O vector size, that's a substantial fraction of a second. That is 50 milliseconds. Since I'm bad at doing arithmetic in my head, let's use the sams2ms object, and we'll ask it 2048 samples equals how many milliseconds at the current sampling rate? 46 milliseconds. If the sampling rate were a little bit higher, then 2048 samples would be a little bit fewer. only 42 milliseconds. So stamps to MS knows the sampling rate and just basically does a division, but it does a division much better than I can do in my head. So if you've got a 2048 sample I/O vector size, then the hardware spends 46 milliseconds gathering up audio. So like audio is happening in real time. My voice is talking and nothing's getting into Max, where the hardware is just saying, hey, I need more samples, I need more samples, I need more samples. Okay, now 46 milliseconds have passed. It gives those samples to Max. Max does its thing. 46 milliseconds worth of audio comes out of MSP, the next 2048 samples of the I/O vector, and that goes to the hardware. So if we make just a very simple input going directly to output patch, this is a really good way to get feedback. There's a characteristic squealing sound of the crappy speaker built into a laptop being picked up by the crappy mic in the laptop. But we don't have to worry about that now because my audio is actually not coming out of my laptop at the moment. So if we turn this on, hello, hello, you can hear that echo, and it's a pretty long echo, whereas if I make this I/O vector size smaller, hello, hello. You see it's a much tighter echo. So there is always latency when you're dealing with digital audio, and the amount of latency depends on how big you make the I/O vector size. So here's a big delay that's putting a lot of time between when I say something and when the same thing comes out of Max, and here with a low I/O vector size, that delay goes down to just over a single millisecond. So basically, you want to use, if you're doing something interactive where you need to respond to sound as soon as possible after it comes in, like for example, if you're using Max as an effects unit and you want to plug your electric guitar into it and jam out on your guitar and have the sound come out of Max into your amp, you probably want the lowest I/O vector size that you can get away with. As you get it to be really low, the same patch ends up costing more CPU time. So you may find yourself needing to turn up the I/O vector size if you're running at the limit of the capacity of your computer. You might start to hear little clicks or glitches or audio dropouts or something as MSP occasionally fails to produce the right number of samples in the right amount of time. So that's why Max lets you set these numbers. So how does MSP do its job? I just told you that it receives a block of samples from the hardware, and you get to set the size of that block. So let's say it's 64 samples. So boom, 64 samples just happened. We now have that data from the outside world. What do we do with it? Well, so we talked about how there's a directed acyclic graph of all the signal connections in your Max patch between all the MSP objects. And we talked about the fact that you are not allowed to have a loop anywhere in this graph. If there is a loop, then basically to compute, let's say A is connected to B and B is connected to A. So to compute A, you need to know the output of B, but to compute B, you need to know the output of A. So it's a sort of logical contradiction. So we saw how MSP just gives up and it doesn't compute A or B if you wire them in a loop like that. It enforces this restriction that it's a acyclic graph, a DAG, directed acyclic graph. So then once you've thrown away all the objects that are part of cycles, then Max does a topological sort on this graph and it finds a linear sequence where it can compute the first object and then the second object and the third object and can go down the sequence with the confident assurance that any object's input will be computed by the other object that's connected to its inlet before that object has to do its job. So what does life look like for a single MSP object? What's a day in the life of the object? Well, it's got inlets and outlets. It's got there's a sampling rate and there's a signal vector size. So each of those inlets receives the signal vector size worth of samples at a rate that's determined by the sample rate. So let's say it's 44,100 samples per second and 64 samples per buffer per signal vector. So the object receives this vector of 64 samples. These represent samples of its input signal, and it does whatever it wants internally, does whatever processing to compute the output samples of this object, and those are also in a block whose length is the signal vector size. So the object is just waiting to do its job, and it gets the go-ahead to do its job when its turn comes in the topologically sorted linear sequence of all the signal objects in the patch. And at that point, all of the input samples are known. So the code that does the signal processing has access to one signal vector's worth of samples for each single inlet that the object has, and its job is to produce one signal vector size worth of output for however many signal outputs it has. The last part of Max is jitter. Again, jitter was originally a separate product, but now it's been fully integrated into Max. And jitter sits on top of Max and works very well with a lot of the existing mechanisms for program structure. So jitter matrices are just messages that flow through Max. They have a special kind of looking patch cords, these green and black ones that we see when we connect jitter objects to each other. But the data flowing through those patch cords, it follows all the rules of the Max scheduler. So for example, there's an object in Max called switch that lets you have, you give an argument for how many inlets you want. We'll just do like another boring example with number boxes. And this object has two inlets. So if we send it the message 0 in the left, then nothing comes out of it at all. It's totally closed. If we send it the message 1, then that makes this first inlet, counting from 0, be the one that gets to talk to the output. So things that come in this inlet have no effect because it's this one that's currently active. But if I make it a 2, then this one has no effect because it's this one that's active. So this object can switch ints, floats, symbols, lists, bangs, and also jitter matrices. So here's an example of using switch with jitter matrices. So these are all built-in movies that come with Max, basketball, chickens, and dishes. And here's a switch object just like the one we just saw that is currently closed. But if we go to 1, we get the basketball movie. If we go to 2, we get chickens. 3, we get the dishes. And 4, we get nothing because there's nothing plugged in to the input here. So there is no jit.switch because you don't need it. Because the switch object, which programmatically makes and breaks connections between its various inlets and outlet, can pass a jitter matrix through itself just as well as it can pass an integer through itself. So a lot of the kinds of things that you might need to do in jitter, you can just do using Max objects. So here's just one example of that. Another important part of Max that jitter piggybacks on and inherits functionality from for free is what's called the low priority queue. Max's low priority queue handles tasks such as drawing to the screen and processing user interface events like clicks and keystrokes. And if you're doing video processing in jitter, you almost certainly want to time it using this low priority queue. So in the documentation for Max, there's this page called Advanced Scheduler Settings that explains this. So you can set all these parameters, and this page tells you what that means. So here it says a low priority queue includes redrawing the screen, and there's a mode called overdrive that changes the priority of timing and MIDI versus screen drawing and user interface tasks. Max has a throttle that makes it not try to do infinitely many tasks all in one go. So when the scheduler says, hey, all my metronomes are supposed to tick right now, I have 1,000 metronomes, they're not supposed to tick, the pull throttle will say, well, I know it's all supposed to happen right now, but I can't do too many things at once. I'm only going to do 100 or 50 or the default is 20 in one moment, and then very shortly thereafter the scheduler gets another chance, it does the next 20 and the next 20 and so on. So there's all these throttles. There's the refresh rate, which determines how often the screen gets redrawn, and finally there's the scheduler slop, which allows the scheduler to say, well, you asked for this to happen 1 second in the future, but I ran out of CPU time, so I'm going to make it 1.01 seconds in the future, but don't worry, I'll catch up. So it's kind of like a stretchy, rubber bandy way of dealing with time where Max makes it happen as close as possible to when it's supposed to happen, and maybe a few events are a little bit late, but time keeps on ticking, and eventually things calm down for the CPU and it gets back on track, as opposed to just flat out falling behind. So if your slop is really tight and you're trying to do more than your computer can do, then time just slows down as a whole for Max and it never catches up. So if you're within the slop, it's like a little elastic notion of time that you can be a little bit on the late side but make it up later. Whereas if you go outside the slop, then Max just kind of has to slow down everything and say, well, I declare that those last 3 seconds were really only 1 second, and I'm going to carry on, and we lost that time, and too bad, it's in the past. So you can think of there being three schedulers within Max. There's the high priority scheduler, which handles things that happen in the future and also things like MIDI events coming in. There's the low priority queue, which handles things like refreshing the screen and also anything that you choose to make happen in a low priority queue, which I'm going to show you how to do in just a moment. And there's the MSP scheduler, which is the synchronous continuous signal processing that every time one IO vector's worth of time passes in the real world and audio hardware says, here's your next 64 samples, and all the MSP objects have to read in their 64 samples of all their input signals and write out their 64 samples of all their output signals, where it doesn't have to be 64, you set that as the IO vector size, as I just mentioned. So those are the three schedulers, and this table that I made shows how to get between these different schedulers. So the rows of the table are the different schedulers that you're going from, and the columns of the table are the different schedulers that you're going to. So let's just take it in order. So this upper left-hand cell of the table is for getting between the max scheduler and the max scheduler. So something that's already on the high priority queue. So let's say a MIDI event comes in. The processing of that MIDI event is in the high priority queue, and if let's say it's a note in object, so and that's connected to various arithmetic that's going to look at the note and decide what to do. So everything that comes out of that object is still going to be processed in the high priority queue. So by default, once you're in the high priority queue, you're going to stay in the high priority queue, and all these different objects that are taking in messages and outputting messages and so on, the whole first traversal of the tree of max objects that are processing this message, that all will stay within the high priority queue. Let's look at this next column to the right, going from the max scheduler to the MSP scheduler. So that's what happens every time you send a message into a signal processing object. So if you are adding a floating point constant to a signal, then the signal input is coming continuously via the MSP scheduling mechanism, but the floating point number comes whenever it does from the max scheduler. And so what happens is that object has a method that is responding to the float that comes in, and it's going to invoke that method in the max queue. The max scheduler is going to say, okay, here's a new floating point number for you plus tilde object, and in that thread, within that scheduling regime, the plus tilde object says, oh, okay, the float that I'm adding is now 3.2, and it stashes that away in its memory. And then the next time that it's asked to do signal processing, then it looks in its memory and it sees that the number that it's adding is now 3.2. So there's this sort of buffering of data that comes in from max into a single object. Any message that comes in from max to a single object, basically it goes into the memory of that object, and it takes effect on the signal processing of that object on the next signal vector. So this upper right-hand cell shows a few ways of getting from the max scheduler into the low priority queue, or the jitter scheduler. So there's an object called defer, which doesn't seem like it does much because you put in a value and the exact same value comes out. Seems like a pretty boring object. But what's happening is that the defer object is taking in a value and then inserting a task into the low priority queue that says output that same value. So an urgent message comes in and defer says, you know what, this isn't that urgent. Put it on the low priority queue, do some other stuff that might be more important, and then later, when max services the low priority queue, we'll have this 49 number that we just threw in, and that's when we'll output. The defer object actually puts it at the front of that queue, so that it's going to be the very next low priority thing that happens. So there's an even more deferring way to defer something called defer low. That, again, if you just use it by itself in a patch, it doesn't look like it's doing anything. It's just outputting the same thing that it receives in its input. But it's the same story about deferring the message onto the low priority queue, but in this case, it's to the back of the low priority queue. I do not like the names of these objects. Both of them talk to the low priority queue. This should be called defer low front, and this should be called defer low back, because they both schedule for the message that they received to be output when the low priority queue is doing its thing. But here it's going onto the front of the queue. It's going to be the next thing that happens. Whereas here it's going onto the back of the queue. It's going to be the last thing that happens. So there's already a bunch of stuff in the queue. The difference between these can be significant. There's also an object called QLim. The QLim object is, as the help patch here says, like a combination of an object called speedlim also with the defer low object. So speedlim is a nice object, which is in the C also here, that says don't output any faster than some minimum amount of time between outputs. So if this is set to 250 and I scroll this thing, you can see that the input is changing more often and the output is only changing every 250 milliseconds. So every time I output something, it says, okay, I'm not listening, I don't hear you, nothing's happening, I don't want anything else to happen. And then finally 250 milliseconds later, it says, okay, I'll output the next thing. Okay, so if I go if I hit the up arrow twice, I go 2, 3. That wasn't very dramatic. Let's make this a higher number. Okay, so this object is never going to output more than once per second. So 1 happens immediately because nothing's happened in the last time. And 0 happens immediately because it's been more than a second since the last time I did something. But if I go 1, 2, 3, then the 1 happens immediately because we were outside of that 1 second window. And then the 2 just gets totally swallowed because it came in the period of time that it was waiting after outputting the 1. And the 2 came in, but then the 3 came in after that. So it's the last one wins. So it forces things to not happen too fast, hence the idea of a speed limit. But this all happens within, it actually all happens within the high priority scheduler on the max side. But if you want it to slow down the rate and also go onto the back of the low priority queue, then that's QLim. So I already explained defer low, and I just explained speedlim. So QLim is just like, as it says here, like speedlim into defer low. There's Q metro, which we talked about. It's just like a regular metro. You tell it to output a bang every so often, if you can spell metro. And when you turn it on, it outputs bangs at that rate. And Q metro does exactly the same thing, except that the output of those bangs happens via the low priority queue. So this is how you're supposed to time your jitter patches. A very, very large fraction of the world's jitter patches. At the top, there's a Q metro that's trying to achieve a certain frame rate. So if you want your patch to run at 30 frames per second, then you set the Q metro's interval to 1000 divided by 30, or 33, meaning that you want the next frame every 33 milliseconds, if possible. But if it doesn't get around to it, then it just doesn't get around to it. So if we have some huge amount of processing happening in the patch, then this Q metro will slow down. Here, let me see if I can just quickly make a huge amount of processing. We'll have an Uzi object, and we'll ask it to output 1,000,000 bangs. Actually, let's start with 10,000 bangs. I don't want to get too crazy. And each of these numbers, we will multiply by 2 and put into a number box. So keep your eye on this flashing button and the rate that it flashes. And when I click on this 10,000, that happens really fast. If I make it 100,000, it's still pretty fast. If I make it 1,000,000, it's still pretty fast. If I make it 10 million, then you see the clicking stops. Max is too busy dealing with these 10 million numbers. And so the Q metro just takes a little pause before it continues. So that's what Q metro is for. So as you just add more and more processing to your jitter program or to whatever is connected to the output of this Q metro, then the rate at which the metronome goes will slow down as necessary to allow all the other things that Max is doing to still be high priority. So now let me say, this is a point I want to reemphasize, this button is happening according to the low priority queue. And if we connect that button to a counter, then this counter's processing is happening according to the low priority queue. So everything that is in this chain, until you go through some object that goes between the low priority queue and some other queue, I mean, if this number went into a cycle tilde object, this is a pretty bizarre composition where we're increasing the frequency by 1 hertz every so often, and that rate of increase slows down when Max is trying to do a lot. So this is an example of getting between, in this case, the low priority queue, not because this number box is necessarily in high or low priority, not because this counter or button are necessarily in high priority or low priority, but because all of this computation is being triggered off of the low priority queue thanks to queue metro. So everything in it is in the low priority queue until we get to cycle tilde, which does its job in MSP scheduler. And so when it finally receives this 125 integer, which is going to set it to 125 hertz, then it stashes that away in its memory, and the next time audio happens, it will synthesize the sine wave of that frequency. So back to this table, just for now we're going to skip the middle row, and we're going to talk about getting from the low priority queue into these other scheduling modes. So this is one of the great ironies of Max. The object delay that's supposed to make something not happen right now, supposed to make it happen in the future, works using a high priority queue. So if you delay something by 0 milliseconds, you'll actually make it happen faster than if you didn't delay it at all. So if you have some events that are being processed in the low priority queue and they hit a delay 0, or a pipe 0, then that promotes them out of the low priority queue into the high priority queue. Again, looking at this next column, getting from the low priority queue to the MSP scheduling, then whenever the low priority queue finally manages to send a message to that MSP object, it's the same story as before. MSP saves the value, and then the next time signal processing happens, it uses that saved value, just like getting between Max and the MSP scheduler. And then to stay within the low priority queue, to get from the jitter scheduler to the jitter scheduler, then you don't have to do anything. Once the low priority queue gets its hands on a message, then by default, everything else subsequently triggered by that message will stay in the low priority queue. So in other words, if you put a queue metro at the top of your jitter patch, then that's the last thing you have to think about with a low priority queue. You know that you're timing everything off of that metro, and you can have dozens, hundreds of jitter objects that are all doing this and that with every matrix, and no problem, it'll all happen in the low priority queue just like you want. Okay, finally, how do you get from the MSP scheduler to the other two schedulers? So this occurs when you have a single object that outputs events. So for example, there's an object called snapshot tilde that will read out the value of the current value of a signal every so often. So signal has a very large number of floating point numbers. The snapshot object says something like, well, every 300 milliseconds, tell me the current value of the signal, or whenever I send you a bang, tell me the current value of the signal. And these typically don't output more than one event per single vector. So even if you set snapshot to go as fast as possible, it will give you a single floating point number per single vector. So any of these objects that output events, they do so using a regular Max high priority queue. If the single objects are talking to each other with signals, then that's the normal situation of the MSP scheduler. And I don't believe there's any way to go directly from an event output from a single object into the low priority queue. So you would output it, and then you would pass it through one of these objects, deferred, deferlow, qlim, or jit.qball, if you wanted to take something that's being produced by MSP and run it through the low priority scheduler. So that's our table, 3x3 grid of the three schedulers and the different ways of getting data, of not really getting data between the schedulers, but getting the flow of processing control between those schedulers. So if Max is doing its thing and you want something to happen via the low priority queue, then that's what this table tells you how to solve. Okay, well, there's been a lot of information in this session. Let's review what we talked about. We talked about the rules of Max evaluation. You got a much deeper understanding of exactly how Max deals with your programs. We talked about files. We talked about Max's search path and how it looks for files. We talked about installing files using packages. We talked about saving your own files in the search path. We talked about different kinds of files that you might want to have in your search path: image files, sound files, MIDI files, collections, dictionaries, all these sorts of things. We looked at various objects that can read and write all these files programmatically in Max. And then finally, in my mind, perhaps most importantly, we talked about abstractions, which are files that contain Max code, Max objects that you wrote yourself in Max. So we're going to be using abstractions quite a bit in the rest of the class. So I feel like we've really been through all of the fundamentals of Max. I think you know all the pieces that you're going to need. There's of course lots of more objects you're going to learn, lots of more shallow knowledge that you're going to need in specific to do particular things that we haven't seen yet. But just in terms of the big picture, in terms of your deep understanding, your mental model of what's going on in Max, what it can do, how Max objects can talk to each other, how to structure programs, how to make your own objects that you can think about later, you're there. You've been through it. So the rest of this class, we're just going to put these ideas together in different ways and look at a lot of very fun and advanced examples of what you can do with Max.